Welcome to our discussion on doubling time and half-life. So building on our discussion of exponential growth and decay, we can now talk about the very widely used and specific times of doubling time and half-life or halving times. It's basically how long will it take for this thing that is growing exponentially to double, or how long will it take this thing that is decaying exponentially to have half as much stuff. And usually the most important kind of half-life is radioactive decay. How long will it take for radioactive materials to get to a safe level? And that's based on their half-lives. So after any time t, right, so after a specific time t, an exponentially growing quantity will reach a doubling time of what we call t double. And it increases in size by a factor of 2, right? So the new value of the growing quantity is related to its initial value at time t0 by the simple rule of the new value is always the initial value times t over 2 to the t double, right? So it's basically 2 to this stuff. So let's put some numbers in here so it makes a little bit more sense. Compound interest produces exponential growth because an interest-bearing account grows by the same percentage each year. So suppose your bank account has a doubling time of 21 years. By what factor does your balance increase in 50 years? Well, the doubling time, the t double, is 21. And so after t equals 50 years, your balance increases by a factor of 2 to the 50 over 21. And 50 over 21 reduces to 2.38, blah, blah, blah. And you just take 2 and raise it to that decimal power, and you get that it's basically 5.21. So it's 5 times as big as what it started. So if, for example, you started with $1,000, in 50 years, it will grow to 5,210. That's how this idea works. Now, if that math seems difficult, and it really isn't, but I don't think it was presented in the easiest way. There's an approximate rule of 70. So for a quantity growing exponentially at a rate of p%, right? So 10%, 7%, 3%, 20%, whatever it happens to be, the doubling time is approximately 70 divided by that p. So this approximation works best for small growth rates. It breaks down for growth rates over 15%. So again, it only works for things basically 15% and smaller. So if you wanted to know the approximate doubling time for the population, when we know that the growth rate was 1.1% per year, we could use this approximation to figure out that doubling time. So we substitute in 40 years, right, was how long it took to double, and we find that 70 over 40 gives us 1.75 per year. So the average population growth rate between 1960 and 2000 was about 1.75% per year. And this is significantly higher than the 2012 growth rate of 1.1%. So exponential decay and half-life is the same idea, but instead of multiplying by 2, you're multiplying by a half. So you can see that the formula is still the same. It's something raised to the t over t to the half. In this case, instead of 2 raised to that, it's 1/2 raised to that. It's just that simple. So radioactive carbon-14 has a half-life of about 5,700 years. It collects in organisms only while they are alive. Once they are dead, it only decays. And this is what they use for what's called carbon-14 dating to figure out how old something is, right? So if you find a bone, then you can date it, calculate how much carbon it has in it, and then based on how much it had when it was alive, you can figure out how old it is, how long it's been. So we can plug the 5700 in for the half-life, and then the initial amount remaining after 1,000 years, right, is going to be roughly that. So for example, if the bone originally contained 1 kilogram of carbon-14, the amount remaining after 1,000 years is approximately 0.885 kilograms. And so they can sit there and they can measure how much carbon-14 is actually in a fossil and then work backwards to figure out what this top number is, and then they know how old it is. Suppose that 100 pounds of plutonium-239 is deposited at a nuclear waste site. How much of it will still be present in 100,000 years? Well, we have to know the half-life of it, which is 24,000 years. Given an initial amount of 100 pounds, the amount remaining after 100,000 years is simply just 1 half, and then we're going to have T over T half, so 100,000 over 24,000, which becomes roughly 5.6 pounds. About 5.6 pounds of the original 10 pounds will still be present in 100,000 years. Now, just like we have approximate doubling time, we have approximate half-lifing with the 70 over P, and again, it only works for small things up to 15%. So suppose that inflation causes the value of the Russian ruble to fall at a rate of 12% per year relative to the dollar. At this rate, approximately how long does it take for the ruble to lose half of its value? Well, since 12% is less than 15%, we can go ahead and use this rough approximation, and we know that it's going to be 70 divided by P, which is 12%, right, per year, and then we get 5.8 years. So the ruble will lose half of its value in roughly almost 6 years. Now, exact doubling time and half-life formulas are a little bit more complex. They use logarithms, but they're still pretty easy, especially if you have a calculator. So for more precise work, you'd want to use these exact formulas. And then you would use the fractional growth rate of the rate equals P over 100. So for an exponentially growing quantity with a fractional growth rate of R, the doubling time is simply log 10 of 2 over log 10 of 1 plus R. And log 10 in your calculator is just going to be log, L-O-G. Any calculator that has a button that says L-O-G, that's base 10. Base 10 is the standard log, and if you see a little button that's LN, that's the natural log, which is base E. But we're using base 10 here. So you have just log of 2 over log of 1 plus R. Again, not that complicated, just sounds that complicated, but once you plug some numbers in, you see it's not so bad. So a population of rats is growing at a rate of 80% per month. Find the exact doubling time for this growth rate and compare it to the doubling time found with the approximate doubling time formula. Okay, so the growth rate of 80% per month means your P is 80 per month or your R is 0.8 per month, right? This should say 80%, not 80. The doubling time, in fact, I should put a little percent in there right now so we know it's 80%, right? Okay. So the doubling time is simply just log of 2 over log of 1 plus 0.08, sorry, 0.8, which is just log of 1.8. So you do log 2 in your calculator, you get this. You do log of 1.8, you get that. You do the ratio of those, right? The top number divided by the bottom number, and you get approximately 1.18. The reason why this is approximately is because this decimal goes on and on and on and on, and we had to round it. So 1.18 months, or about 1.2 months. Now the approximate doubling time formula would be 70 over P or 70 over 80 or 0.875 months. And you can see the approximate formula does not work well for large growth rates. We said it fell apart for anything above 15%. So that's why we need to use the exact formula. And really, we should always be using the exact formula because it's really not that difficult. So this is the formula you want to memorize, and this is the formula you want to use.